We had 2 sets of homework last night. First of all, it was page 681, practice problems number 1 to 3. And then we had worksheet number 18, both on curved lenses. Let's take a look at the practice problems first. Any issues with those 3 questions on page 681, please? The other classes were both asking me to go over question number 3. Do you guys need number 3, or are you guys okay? Yes? Yes? All right, let's take a look at number 3 then. Any others? No? All right, let's go over number 3 then. It says a projector uses a converging lens. This is what I do. When I see the words converging and diverging, I circle them, and then I indicate whether it's positive or negative. Now, if it's converging, it's positive. If you forget to circle it and you forget to worry about positive or negative, well, you're still going to get it right, because by default, you're going to make it positive. But I think it's a good habit to remember to circle converging and diverging, because if you start circling both of them, then you're less likely to forget to circle the diverging, which is the one that's really important. So just get in the habit of it. Make it F as positive, even though if you forget to do that, you're still going to get the right answer here. The image is focused on a screen that's located 5 meters away. The image is generated from a slide that's located 7.5 centimeters from the lens. I'm circling both of those, not because they're necessarily odd units. I'm allowed to use either one of those units in the equation that I'm about to use. But the problem is I'm not allowed to use both. So I'm circling both of them to remind me that I've got to either go centimeters for both of them or meters for both of them. And it doesn't matter which one. We're going to find the focal length of the lens, and we want to find the magnification. Let's circle a couple of our givens here now. This 5 meters, what does that correspond to, please? Is it F? Is it DO? Is it DI? DI, good. The focused image is on that screen. Now, it doesn't mean just because there's a screen that there's an image there. But this tells us that there is an image there, right? If there is an image there on that screen, then it's got to be the image distance, okay? If you didn't see an image, sorry, if you saw a screen and the image wasn't there, well, then you can't call that the image distance if there's not an image projected onto the screen. There is here, so let's call it DI. The image is generated from a slide that's located 7.5 centimeters from the lens. What are we going to call that? It's not DI. It's going to be DO, right? And we're looking for F here, and we're also looking for the magnification. Now, what would you rather do? Go centimeters or meters for both of those? Doesn't really matter. I'd probably go centimeters myself, because I think for whatever reason it seems easier to multiply 5 by 100 than it does to divide 7.5 by 100. So I'm going to go both meters, but if you're more comfortable going the other way, that's fine too. DI is therefore going to be 500 centimeters. DO is 7.50 centimeters. We're looking for F, which we know is a positive value, and we're looking for M, the magnification. Let's use the lens equation. And let's solve for F now after we sub in our values here. We get 1 over 7.5 plus 1 over 500. Let's pull out the calculator and see what we can do with that. Let's see, 7.5 x to the minus 1 plus 500 x to the minus 1 gives me 0.135. Let's not forget to flip that over. I wouldn't be surprised if this was a multiple choice question on a test. I wouldn't be surprised if 0.135 was one of your answers for F. Because that's probably, I would think, a fairly common mistake. You get this far, you just forget to flip that over. Okay, let's not make that mistake. Let's flip that over, and let's get 7.3892 for the focal length. Now, I'm leaving it, I'm going to round it, but I'm going to also record my unrounded number just in case I need that later on. It becomes 7.39 centimeters as our rounded number. Now let's find the magnification. There's 2 ways that we can do that theoretically, HI over HO, but we don't know either HI or HO. Or we can do negative DI over DO. Don't forget the negative in front there. It becomes negative 5.00 centimeters, 500 centimeters, I should say, over 7.50 centimeters. And when we do that, it works out to be negative 66.7. So it's 66.7 times the size that the actual object was. Now, what about the characteristics of this? Here, we're not asked to find the characteristics, but tell me whether it's a larger, smaller, same size image. If the magnification is 67, then the image is going to be much, much bigger than the object is, right? So we're going to say larger. We know that the image is right side up or upside down. What is it? Why do you say that? Okay, you see F is positive. That tells us that it's a converging lens. Okay, the fact that M is negative tells us that it's going to be upside down. Okay, upside down relative to the object, we get a negative M. We get we have a DO that's positive. It's projected onto a screen, so that tells us that it's a real image, even though we're not asked to find that. Right? Second bit of homework we had last night was worksheet number 18. The answers for that are up here now. Let's take a look at those and make sure that you've got correct answers. Then you can let me know which question or questions there that you'd like me to go over. Request to go over question number 3 here from worksheet number 18, so we'll do that now. 3 says, the image created from a 10 centimeter tall upright object. And we see that it's an upright object. That means that HO is going to be a positive value. That's not a big leap for us because HO is almost always a positive value for us. But we have that information, so we'll write that down. It's placed 5 centimeters from a lens that's 4 centimeters. The image is 4 centimeters tall and upright. So we're going to say that HI is also a positive value. That's probably a little bit more important than saying DO is positive. DO is almost always positive. HI is positive about half the time. We have an HO that has a value of positive 10.0 centimeters. We have a DO that's positive 5.00 centimeters. And we have an HI that's 4.00 centimeters. We want to determine the magnification, the image distance, the focal length of the lens, and we want to find the attributes as well as the type of lens used. Now let's do those calculations, and that should be enough to tell us the rest, the attributes and the type of lens used. I like to start off with 1 over DO. 1 over F is equal to 1 over DO plus 1 over DI. But since I only have one of those variables here and I'm looking for 2, I'm going to probably start off with my magnification equation. M is equal to HI over HO equals 4.00 centimeters over 10 centimeters. That gives us a magnification of 0.40. 0.400. Let's use that magnification now to find DI. We know that M is equal to negative DI over DO. That means that DI is equal to negative M times DO, which is negative 0.400 times 5.00 centimeters. That gives me 2, or negative 2.00 centimeters. Now that we have DI, we can use that other equation, that lens equation, 1 over F is equal to 1 over DO plus 1 over DI, to solve for F. Let's do this one on our calculator as well. Let's say 5x to the minus 1. I'm going to subtract from that 2x to the minus 1. Aren't we adding a number there? Aren't we adding 1 over negative 2 as opposed to just subtracting 1 over 2? Isn't that the same thing? It doesn't matter where we put the negative, whether it's with the 2 or the 1. It doesn't make any difference in the top or the bottom. Okay, if it's on the top, then you could, I think, fairly easily see that 1 over 5 minus 1 over 2 is the same thing as saying 1 over 5 plus negative 1 over 2. It's the same thing. Let's get that number there. Remember that that's not our final answer. Let's flip that over to get the focal length. And when we do that, we end up getting negative 3.33 centimeters. Now, let's first look at the type of lens we have. Since we have a negative focal length, it tells us that we have what kind of lens? Converging or diverging. You can still look back at those. You can still look back at that table if you want. What kind of lens do we have if we have a negative focal length? Diverging, right. Whether we're talking about lenses or mirrors, negative f means diverging. Okay, so it's a diverging mirror. What about the characteristics now? Larger, smaller, same size. Well, the image is 4, the object is 10, it's going to be smaller. Upright or inverted? HI is positive, HO is positive. They're both upright. And finally, is it real or virtual? How do you know, Christine? Good. If DI is negative, it's a virtual image. Okay. Good? Dylan, is that good? Any other questions on that page? No? All right, then. I'm going to give you a few more questions to work on for homework tonight, but I'm also going to give you a few minutes to work on them in class today. Those questions that I'd like you to do for homework are page 683, number 1 to 2, and 8 to 20. So it's quite a few questions. I think it's 14 or 15 questions. And that's why I'd like you to give you a little bit of a head start right now so you don't have quite as much to do tonight. So let's see what we can do with those over the next 9 or 10 minutes, and then we'll move on to our new topic after that. All right, let's move on to our next topic here now for the last few minutes of class. We've talked about refraction in quite some detail over the last few days. Refraction was the bending of light. When light enters a new medium from an old one, the speed will change. As a result of the speed changing, the wavelength will change. But the angle will also change. That bending or that change in the angle is known as refraction. Now we're going to talk about a new one called diffraction. You learned about this a little bit last year in Physics 20, and we talked about it the very first day of this unit. But not as much detail as we're going to talk about it today. Diffraction is not the bending of light, rather it's the spreading out of light, or of any wave, but particularly for us in this unit, light or EMR, as it goes around a barrier or through an opening. I've got a good picture here of diffraction taking place. If we draw that, it would look something like this. There's a barrier that looks like that. There's water waves that are coming from the ocean or from a lake or whatever towards that barrier. Most of those water waves just reflect off of the barrier, but the part that hits the opening in the barrier, or the part that hits the opening between the two rocks right there, keeps going. But notice what the pattern looks like on the other side. Notice what this pattern looks like down here. It's not just that thin, narrow, straight wave. Rather, that thin, narrow, straight wave spreads out so that it looks more circular, like it does in the photograph. That spreading out, or that appearance of the wave looking like a circle, is called diffraction. Now, the amount of diffraction, the amount that it spreads out, is dependent upon a couple of things. The size of the opening, and it's also dependent upon the frequency or the wavelength. We're not going to really concern ourselves with that this year in Physics 30. This is good enough for us as far as diffraction. We're going to take this in a different direction than we did in Physics 20. We're going to talk about it in the context of interference. You don't need to draw this diagram, by the way. Interference is that phenomenon whereby a couple of waves strike each other, hit each other, and they form either a bigger wave or a smaller wave. When two crests hit each other, they form one big crest. That's constructive interference. When two troughs hit each other, they form one big trough. That's constructive interference. But when a crest meets a trough, they cancel each other out. They get no wave. That's called destructive interference. Here we have a wave front, as you can see on the bottom here, and it's traveling upwards here. when it hits this boundary or this barrier, most of it's going to reflect just as it did in the last picture that we showed on the last page. But you see two openings here. Part of the wave is going to go through that first opening, and when it does, it's going to diffract. Part of the wave is going to go through the second opening, and when it does, it's going to diffract. When we have two diffraction patterns now, we're going to get this phenomenon of interference taking place because we're going to have two different waves coming together in the middle. I'm going to draw every second line as a blue line. The blue lines are going to represent crests of waves. The black lines that are left over are going to represent the troughs of waves. So we've got a series of crests and troughs produced by that first opening. And we're going to have a series of crests and troughs produced by the second opening as well. Remember, blue lines represent crests, black lines represent troughs. When blue meets blue, or when black meets black, in other words, when crest meets crest or trough meets trough, we're going to get constructive interference. So what I want to do right now is with my red marker, put a little dot everywhere where I see constructive interference. Everywhere where I see a crest meeting a crest or a trough meeting a trough. Blue, blue, black, black, blue, blue, black, black, blue, blue, black, black, and so on. Same thing right here. These are areas of constructive interference. Remember, where blue meets blue or black meets black. Start seeing a pattern after a little while here. It may be, at least. Did I miss one? Top. Oh, right here. Yeah, that should be, thank you, that should be drawn right here, right? Yeah, black and black there. Okay, thank you. Let's join those together. We see some lines here. Let's see what that means in just a second here. Let's draw some green dots here now. These green dots are going to represent areas of destructive interference. So we're going to draw those everywhere where a blue meets a black. In other words, a crest meets a trough. We're going to see that here and here. What's going on right here? Oh, that's blue, right? Start seeing a pattern forming there as well, I think, where we have these green lines in between the red lines. So we have these alternating areas of constructive interference with destructive interference. If these are waterways and you happen to be lying on an air mattress just trying to enjoy the sun, you're probably want to lie on one of the green lines. That's the areas of destructive interference. That's where the waves, the crests and the troughs, cancel each other out. And you're going to be sitting or laying on a calm bit of water. If you happen to be lying on one of these red lines, then you're going to get an area of constructive interference. The crests that you would encounter and the troughs that you would encounter would both be twice as big as they normally would be, because we're producing bigger crests as a result of constructive interference and bigger troughs as a result of constructive interference. So red lines, big crests, big troughs. Green lines, nothing. The crests and troughs have canceled each other out. So if they're water waves, you're going to observe that everywhere along here, everywhere where you see these red lines and these green lines. If it's light waves, you're not going to observe it right in there because you can't see these colors, these light waves, until they strike something, until they refract or reflect off of something. Let's put a screen up here so that we can observe the light rays. On that screen, where the red line hits the screen, you're going to see a bright spot because you've got constructive interference. You've got more light as a result of crest hitting crest and trough hitting trough. We're going to see an area of constructive interference right here and right here as well. Everywhere where we have red lines, constructive interference lines, we call them antinodal lines. We get this bright spot on our screen. Now, in between those bright spots, what do we see? There's nothing there. There's nothing in between them. We call it a dark spot. Everywhere where the green line hits the screen, we see nothing. Can anybody explain to me why we see nothing where the green line hits the screen? What did the green line represent? If the red line was constructive interference, the green line was destructive. And if you have destructive interference, it cancels out the wave. You get no light. The light disappears. A crest of a light hits a trough of a light, the light disappears. So we get a pattern formed on this screen: bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on and so on and so on as a result of constructive and destructive interference. I'm going to pull up a little applet here just to show you maybe what happens here in a little bit better of a way. It's going to come up here any second now. There it goes. What you see right now is a beam of yellow light. It's one color, monochromatic light we call it, one color, versus polychromatic light, which is multiple colors. Here, this yellow light is hitting this screen, but this screen has two cuts in it, two openings in it, two slits in it. This light, as a wave, diffracts through both of them. Now, you can't see the diffraction pattern that's formed, but we know that it's there because diffraction happens when the light goes through both openings. Those diffraction patterns interfere with each other to produce those lines of constructive and destructive interference. The yellow lines that are drawn in here, you wouldn't actually see if this was for real because they wouldn't be reflecting off of anything, but they're there. These yellow lines are areas of constructive interference. In between those yellow lines, there's still something going on, but it's destructive interference. What do we see when it reaches the screen? Well, when the areas of constructive interference reach the screen, we see a bright spot. Then we see a dark spot where the destructive lines hit the screen. Then we see a bright spot where the constructive lines hit the screen again. A dark spot on the other side and a bright spot on the other side of that again. We get this series again of bright spot, dark spot, bright spot, dark spot. Finally, and this is where we'll end it here today, okay? I want to change the wavelength of this light. The wavelength, therefore the frequency of this light. Let's increase the wavelength, which decreases the frequency. We're going to shift from yellow light down to red light. What happens? Well, that middle bright spot is in exactly the same position. It's in the middle. But the other bright spots shift a little bit. The first bright spot on the left-hand side was right here. Now it's right here. The first bright spot on the right-hand side was here. Now it's here. So if you increase the wavelength or decrease the frequency of the light that you're using, you're still going to see the same basic pattern. The same phenomenon of interference will take place, but the relative positions of the bright spots will be different. Now, you can remember that. Or when I give you an equation that describes what's happening tomorrow, you can use that equation to derive that, to figure that out, that the lower the frequency, the higher the wavelength, the further out from the center the bright spot forms. Now, somebody else, I forget whether it was period 2 or period 3, asked a great question. It's a great question. Yeah, I don't think I've ever had anybody ask that question before. What would happen if we don't shine laser beams on it? In other words, what would happen if we shine polychromatic light on it? Not just red light, but we shine red and yellow and orange and yellow and green and blue and indigo and violet. What happens if we shine all the colors of the rainbow on it? Let's take a look at the individual colors again for a second. Let's start with red here. Okay, if we start at 780 nanometers, which is red light, then we get a bright spot formed right here. Let's just take a look at this one bright spot on the left-hand side. Let's shift it down a little bit now to yellow light. Okay, yellow light. Actually, let's go to green light. Let's go to green because I don't have a yellow marker. When we have green light, then we get a bright spot formed right there. Let's shift it all the way down to blue and violet light. Then we get a bright spot formed right here. These three bright spots that we just had formed, let's try to get a different color there. Let's just circle it in blue here. These three bright spots that we just had formed all correspond to the first bright spot. They all correspond to that first antinodal line, or that first line of constructive interference. If we have these colors separate, and we shine just red light on this, then we're going to see the bright spot right there. If we shine just green, then we're going to see it there. If we shine just blue, then we're going to see it right there. If we shine all the colors of the rainbow together at it, we're still going to see bright spot, dark spot, bright spot, dark spot. But the first bright spot won't be blue or red or green. The first bright spot will be a rainbow of red, orange, yellow, green, blue, indigo, and violet. Same thing on the other side. The first bright spot on the other side will also be a rainbow of red, orange, yellow, green, blue, indigo, and violet. The next bright spot will also be a rainbow of red, orange, yellow, green, blue, indigo, and violet. The only difference here between this and a prism, remember a prism can split up light, right? It's called dispersion. The only real difference here between this, which creates the rainbow, and the prism, which creates the rainbow, is that the rainbow creates red first and violet last. Here's my prism. Okay, red light, violet light down at the bottom. This one, you notice, red light, okay, this first one here, red light gets refracted the least. With diffraction, red light gets diffracted the most. So we get these spectra formed, these rainbows formed, but they're opposite to the prism. The prism is red, orange, yellow, green, blue, indigo, and violet. With diffraction and interference, it's violet, indigo, blue, green, yellow, orange, and red. As measured from the center, that is, it's opposite. Does that make some sense? Again, tomorrow when I give you the equation, you're going to be able to figure that out. If you happen to forget, you'll be able to calculate the angle for red light is going to be greater than the angle for blue light. So therefore, you know that red light is going to be diffracted more than blue light, even though it's refracted less. If you remember it, great. If you have to rely on the equation tomorrow, that's okay too. All right, we're going to wrap it up there for today.